Awesome. So this is the EX375 final project recording. In the interest of time, I'm going to try and keep it crisp. I just did a recording that was 8 minutes in length. So quickly, my project was to develop a rigorous understanding of boosting algorithms by reading a selection of papers and providing short code snippets. Papers are listed here. I read them all. Based on those papers, I tried to formulate a structure of the project. This is that structure right here. We're currently in the introduction, and we'll go through all the topics as such. First off, everything emphasized AdaBoost is kind of the gold standards of boosting. Here is pseudocode. I'm not going to brush through the pseudocode and actually just jump straight to the implementation. The implementation is the meat of the project. You'll see comments that reflect the steps of the pseudocode. AdaBoost takes in XYG training percentage and M. X and Y are the actual X and Y samples. G is the base classifier. The training percentage is the split you want in your data, and M is the number of classifier iterations you want to use. Obviously, you don't have to use the same classifier at one stop. You could use other ones, but this is the way I implement it. Step 0 is just pre-processing. You feel free to look at that if you want. Step 1 is when we start getting into it, we initialize a vector of weights where each weight corresponds to a weight for a particular sample in the training space. We then go to step 2. Step 2 iterates across M. We take classifier, fit it according to the training sample and weights. We make predictions off of that. From those predictions, we calculate an error. Interestingly, in the error, it's based off of a 50% classifier accuracy. You can check that in the log and for how it's actually calculated. This error is only important to calculate alpha. So alpha is the weight this particular mth classifier gets. And I'll come back to alpha in a second, but it's very, very important. It's the weight or like actual importance of said classifier in the M step. Next, we update our weights according to classifications. The whole trick of AdaBoost is emphasizing previously misclassified points and using this update algorithm to do so. Once we finish updating, we renormalize our W vector just so things don't get janky, and then we record by appending our current classifier and weight. Then, in terms of my actual implementation, which is where we're going to here, we have the model, which is actually what's returned, which can take in X and make predictions. And if you didn't give a training percentage of 100%, we'll make predictions on the testing set right here. Going to the actual model, it's pretty simplistic. Sorry, I overshot it. Right, we take the sign of every weight, of every classifier and its alpha measure for each example, and then sum that. And you can see that happening in the return math copy sign. And that will give us a prediction for our inputs, right? And feel free to play around with this if you're so inclined. I made a sample call here. So AdaBoost returns a model, so you can call model on a testing example and see how well you do, which is really nice. Awesome. Again, the code is kind of the meat of the implementation. Now into the theory. So we have some similarity between boosting and SVMs, which was established in said paper above. With a high enough understanding, that SVMs can map low-dimensional data into high-dimensional linear separable data. What's interesting, and they do so to maximize the minimum margin. What's interesting is that boosting also tries to maximize minimum margin when the margin is defined as yi, am, gm, and xi. And that's actually similarly defined here in the exact paper. It's just written a bit differently. And this is a great comparison, right? Like from a mathematical perspective, to like be able to equate the optimization and the actual goal of two pretty fundamentally disparate ideas between boosting and SVM is really nice, and we can start to get to some core roots of what's going on. We have boosting and game theory from this paper over here. The main takeaway, right, is just that boosting can be viewed as like a game theory implementation or linear programming. To make the exact analogy, you need to have like rows would be represented as like n examples, right, in our training space, and then we have the columns represent the actual like m classifiers, and then you have a matrix where you can perform game theory operations. Obviously, like there's not a lot of implementation off of this, but the notion that you can apply boosting to like the prisoner's dilemma and create some really interesting like complex games is fascinating, right? Especially if anyone's like an econ person here. And I think it's just a great notion to get into the weeds on boosting. Last is boosting in the future, where there's a paper on deep boosting. Deep boosting was incredibly complex. I've seen about trying to implement it actually, but here's the pseudocode. It was terrifying. If you want to try that, feel free, but I could not. So deep boosting was simply trying to like select classifiers based on their weights and complexity, where K represents the complexity of a base classifier. Algorithmically, they're just trying to select the appropriate number of weights that have been modified. And I don't do it justice here because obviously the algorithm was insane, but it's just again out like classification selection. Lastly, edit boosting was really interesting, right? It gave me a really rigorous understanding that we're just generating decision trees and stumps, and it made me think about investing, right? Because a lot of investors, I think, especially in the startup space, look to like rules of thumb and be like, oh, we need good product market fit. So as a next step, I think it'd be really interesting if we could get Crunchbase data, which is a database of startups, try and predict. Overall, really great project with like clear actionables, clear learnings, and clear next steps. I really enjoyed the class. Thank you so much.